Okay, hi guys. So in this lecture, we'll be starting off on looking at um, the reversible reaction that takes place at non-standard states. Okay, reversible reactions taking place at, rather, I can directly write it at non-standard states. Okay, so we have delta Rg equals to delta Rg naught plus RTLN Q. This is a very important equation that you almost remember by heart. Okay, so this is delta Rg is nothing but change in Gibbs energy of reaction at non-standard state. Change in Gibbs energy at non-standard state. Delta Rg naught is change in Gibbs energy at standard states. And I have suppose you know the R and T. Okay, and Q is nothing but reaction quotient. Okay, so at equilibrium, what we can say, that at equilibrium we can say that delta Rg at a certain temperature and pressure would be 0 at equilibrium, and this is non-standard Gibbs energy. We will be talking about Gibbs energy in detail in our next coming set of video lectures. Okay, if not in this video lecture, then obviously in next video lecture series. This is non-standard Gibbs energy, and Q becomes K equivalent. Okay, so we can write that as delta Rg becomes 0, so we can write delta Rg naught plus RT ln Q becomes K equivalent, so we can write that delta Rg naught becomes minus RT ln K equivalent. Okay, or we can also write for a shortcut that delta Rg naught would be equals to minus 2.303 RT ln. Ln is replaced by log by introducing a factor of 2.303 RT log K equivalent. So we are writing both delta Rg naught in terms of ln and log. Okay, so with this we come to the end of this concept, and we begin a new concept which is nothing but phase equilibria. So let's get started. Phase equilibria. So in phase equilibria, one point or the first point to note is only phase transformation takes place in phase equilibria. Okay, so another point that it is also heterogeneous. Okay, next is let's see the three-phase diagram of the same three-phase diagram of water. So we have this graph. Okay, so let me draw it more bigger. We have a graph here. On y-axis we have pressure in mmHg, and on x-axis we have temperature and degree Celsius. What will the graph look like? That we have a line here, line here, and line here. Okay, so this is nothing but the whole region is liquid, this is solid, and this is gaseous. This unique single point is triple point of water. Okay, and the curves are, this is the sublimation curve, okay, this is vaporization curve, and this is fusion or melting curve. And we know that from S to G the reaction would be directly H2O S2 H2O G, that's why it's called sublimation curve. For vaporization curve we can write the equation would be H2OL converting into H2O G, and for solid to liquid conversion we can write that H2OS converting directly into, or rather converting into H2O, that's why it's called melting curve. Okay, and 1 atm, obviously we know that it is equal to 760 mm of Hg. Okay, so at triple point what happens is all three phases are at equilibrium. This is the triple point. So at triple point we can write that all three phases are at equilibrium. Okay, and temperature at triple point would be 0.01 degree Celsius, and pressure would be 4.58 mm of mercury. Okay, now what we see is H2S directly converting into, or rather converting into H2OL. So for this delta H fusion or melting would be equals to, is rather positive, and delta U change in internal energy would be negative. Okay, so we can write here that, rather we'll be talking about internal energy later point of time, let's not get involved into that, but let's talk about delta V, which is change in density, rather change in volume, change in volume. So delta V here would be negative. Let's see how. So delta V is nothing but volume of H2OL minus volume of H2OS. Now we see that as density of water at 0 degree Celsius is greater than density of ice at the same temperature or at 0 degree Celsius. Water means I mean H2OL, and ice I mean H2OS. Okay, so as the density of water is or H2OL is greater at 0 degree Celsius than density of ice at 0 degree Celsius, then we can say that this implies, as density is inversely proportional to volume, this implies that if density of water at 0 degree Celsius is more, thus that implies that volume of water at 0 degree Celsius would be lesser than volume of ice at 0 degree Celsius. So this implies that delta V would be, as VH2O is lesser than VH2OL, then we can say that delta V would be negative. Change in volume would be negative when the conversion of solid to liquid takes place, or from ice to water take place. Okay, delta V is change in volume. Please remember a single fact that 0 degree to 4 degree Celsius as we go, then density of water in any in means in the water phase increases and volume of the same decreases. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing more concepts on phase equilibria, and till then, good luck and goodbye.